Hi, my name is Mirte van der Eyden and I'm going to tell you about our project on the undecidability of tensor stable positive maps. These results were published last year, you can see that here, and can also be found on the archive. I'm working as a PhD student at the University of Innsbruck in the Institute of Theoretical Physics in the group of Gemma de las Cuevas. And this work is done with Gemma, but also together with Tim Netzer from the Mathematics Institute in Innsbruck. So the project we did lives on the intersection between physics, mathematics, and computer science. And don't worry if you're not an expert in all of them. The only prerequisite for this video is a bit of basic linear algebra. So the motivation of this work comes from physics, where we try to answer a long-standing open problem about entangled quantum states. This problem can be reformulated into a purely mathematical problem. This is a problem about tensor products of sets of positive maps, and this is what we actually studied. And the method that we then use to try to solve this problem comes actually from computer science. Namely, we try to prove that this mathematical problem is algorithmically undecidable. And I will tell you all about this in the rest of this video. So the area of physics that I work in is called quantum information theory. And one of the goals in this field is to find protocols that ensure secure communication of information between two parties that are separated from each other. So maybe one is here in the mountains in Innsbruck, while the other one is somewhere far away, say in the Netherlands. And the reason that quantum theory plays a role here is that secure communication can be guaranteed when the two parties share a so-called entangled quantum state. This means that they both have a particle and that these particles have a very strong correlation called entanglement. And this entanglement can be used to guarantee that no one is eavesdropping on them. And for the most efficient and most secure communication protocols, you need as much entanglement as possible. And therefore the parties are often required to share a maximally entangled quantum state. But in the real world, perfection is of course hard to achieve because both particles also still interact with all the other things around them. And therefore, in practice, it's only possible to create an almost maximally entangled state. And once you have one state that is not maximally entangled, there is no way to increase the amount of entanglement anymore within these particles, within this one state. There is, however, a way to combine the entanglement of multiple copies of this almost maximally entangled quantum state into one copy of a maximally entangled state. And this is called entanglement distillation. And this process, unfortunately, does not work for all quantum states. And since we really need these maximally entangled states for this secure communication, it's very important to classify which quantum states can be distilled and which quantum states cannot. So this name of entanglement distillation comes, of course, from the chemical process of distillation, where you obtain from a large amount of fluid the one small part that is valuable to you. And this is what we do here as well. We combine the entanglement of a large amount of less than maximally entangled states into one maximally entangled state. So let's see for which states we can actually do this. The word quantum state might sound still a bit vague to you, to some of you at least. But luckily there's a very precise mathematical representation of a quantum state. Namely, it is a matrix with certain properties. So any matrix that is positive semi-definite and Hermitian, which I just denote as PSD here, meaning that it has non-negative real eigenvalues and has trace 1, is a quantum state. For example, the matrix you see here. And the numbers in this matrix represent probabilities of the outcomes of some measurements on the particles. Now, the good thing about this mathematical representation is that some physical properties of the quantum states can be translated into mathematical properties of this matrix. And this is also the case for entanglement distillation. Namely, the property of the state being distillable corresponds on the matrix side to the partial transpose. As you know, you take the transpose of a matrix by mirroring it along its diagonal. For a partial transpose, we only transpose the information belonging to one of the particles. This means that we divide the matrix up in blocks and take the transpose of these smaller blocks. So the two blocks on the diagonal now will stay the same, but the off-diagonal blocks will change into this. This is the partial transpose of the matrix. In the picture, we denote it like this here. Now, if the partial transposed matrix is still positive semi-definite, it is known that the quantum state is not distillable. If, however, the partial transposed matrix is no longer positive semi-definite, as is the case for this matrix here, it is sometimes distillable, we know that. It is, however, still a big open problem if this is always the case. So we call this type of state a non-positive partial transposed state, or NPT quantum state. And the open question is then, are there any undistillable NPT states? So are there states for which the partial transpose is no longer positive semi-definite, but at the same time it's not possible to create a maximally entangled state from them? And this problem has been open and researched a lot for over more than 20 years. And this is the open problem in physics that motivated my project, the search for this object, an NPT undistillable quantum state. Now, it has been shown in a paper in 2016 by Alexander Müller-Hermes and collaborators that this problem can be reformulated into a purely mathematical problem. This problem is also still open, and it is the one that I have tried to solve. It has to do with positive maps and tensor products, which I will tell you about now. So we consider linear maps or functions denoted by P, which map square matrices of dimension D to square matrices of dimension D. This means that if you have as input some matrix, like this one here, that it gets sent to another matrix of the same size in a linear way. And during this talk, I will use this here as a picture of a map. You can imagine putting some matrix in here on the top and getting some matrix out on the bottom. Such a map P is called positive whenever it maps every matrix that is positive semi-definite, or PSD, also to a PSD matrix. And we depict a positive map like this in green because it's positive. Also, we will denote that P is positive by just writing it's larger or equal to 0, like on the bottom of this slide. These positive maps are the objects that we study. Now, as I said, the open problem has to do with tensor products. So for matrices, there is an operation to create from two matrices one bigger matrix, and this is called the tensor product. What you do is you plug in the second matrix into all entries of the first one, like we did here. If you then multiply everything out, you're left with a matrix of a size which is the square of its original size. Since we can take tensor products of matrices, we can also take tensor products of the maps P. So the map P tensor P can be seen as one map, which takes as input these bigger size matrices and also outputs bigger size matrices. In the pictures, we denote this by just putting two of the maps next to each other. Then we can imagine putting one big matrix in here on top and getting one big matrix out on the bottom. The type of questions that we are interested in is, if we start with two positive green maps and take their tensor product, is the resulting big map on big matrices still positive? So does it send all big PSD matrices to big PSD matrices? Or is it maybe not positive anymore, as depicted here in orange? Let's look at that question in a picture. What you see here is a picture of the set of all positive maps, with outside all the not positive maps. What we will do now is take a tensor product of such a positive map P with itself and ask the question I just posed. Is their tensor product still positive? It turns out that this is the case for some of the positive maps, but not for all of them. So the set of maps for which this is true is actually smaller than the set we began with. We can continue this and ask the same question for three tensor products. This can again be seen as a one big map on even bigger matrices. And again, the set of maps that stay positive becomes slightly smaller. We can go on, and we can ask, are there any positive maps P for which all the tensor products are still positive? And we call those maps tensor stable positive. So for all n, the nth tensor power will still be positive. And it has been shown that there are two classes of positive maps for which this is indeed the case. The first class are the completely positive maps. And these are maps that are not only positive, but have the extra property that if we take the tensor product of P with the identity map in any dimension, the full map should still be positive. These completely positive maps are tensor stable positive, and this is still the case if we compose them with the transposition map, leading to the set of completely co-positive maps. These sets of maps are very well understood and are easy to characterize. And therefore, we will call these maps of tensor stable positive maps, the ones we know, the trivial maps. and we denote them like this, in extra bright green, because we know that all their tensor products will still be positive. They're like super positive. The big open question here is, are these the only ones? Or are there more bright green but non-trivial maps that are tensor stable positive? We depict these maps like this. Because all their tensor powers are still positive, but they are a bit weird and twisted. We don't know what they look like yet. They are not trivial. So the question is, does there exist a non-trivial tensor stable positive map? And what is shown by Alexander Müller-Hermes in 2016 and his collaborators is that if there exists such a non-trivial tensor stable positive map, this means that there exists also an NPT quantum state that cannot be distilled. They show this by explicitly constructing a quantum state with these properties from the description of the non-trivial tensor stable positive map. However, it remains open so far if either of them exist. So we are searching for these NPT undistillable quantum states because we wanted to understand which quantum states can be used for secure communication. However, to find them, we can also focus on finding a non-trivial tensor stable positive map. And this is what I tried to do in my work. And I will now tell you how I tried to use methods from computer science to try to solve this problem. So, in computer science, in particular the field of computational complexity, one studies how much resources are needed to compute a problem. It turns out, however, that some problems are not computable at all. There cannot exist an algorithm, or officially a Turing machine, that can solve every instance of the problem correctly. And these problems are called undecidable. So how can you show that a problem is undecidable? Well, first of all, you need to phrase it as a decision problem with a yes-no answer. So a computer cannot answer the question, are there non-trivial tensor stable positive maps? Therefore, we rephrase it as, given a positive map P, is it tensor stable positive? An algorithm for this problem would get as an input a description of a linear map and has to decide if it has this property of being positive for all tensor powers. Namely, if it is one of these types of maps. Otherwise, it should output no. We will call this problem TSP for tensor stable positivity. So why would we try to show that this problem is undecidable? How does that help us in finding the things we want? Well, I'm now going to argue that if we prove undecidability of problem TSP, this actually implies existence of the non-trivial tensor stable positive maps, which in turn implies existence of these quantum states that we are looking for. So why does this implication hold? Let us assume for a second that there are no non-trivial tensor stable positive maps. So the only possible types of maps are the trivial ones, just normal positive maps that are not necessarily tensor stable positive, or even maps that are not positive at all. So in this case, we can write down an algorithm for problem TSP, and it would go as follows. Given a map as an input, the algorithm needs to check if this map is of the trivial type, so if it's completely positive or completely co-positive. And as I said, these properties are very well understood, and there exist relatively easy ways to check this. And therefore, if the map is trivial, the algorithm can output yes. Since these are the only ones, in all other cases, the algorithm would output no. So from this we conclude that if there are no non-trivial tensor stable positive maps, the problem is decidable. Namely, there exists an algorithm, and it's exactly the one that I described here. So let's look again at this statement. If none of the non-trivial maps exist, the problem is decidable. This statement has the logical form, if not A is true, then B is true. So if we take the contrapositive of this statement, we get, if not B is true, then A must be true. So in our words, that means, if problem TSP is not decidable or undecidable, then the non-trivial maps must exist. And this is exactly the implication that we need here. So if we manage to prove undecidability of the problem, we show existence of the non-trivial maps and therefore existence of these quantum states. Okay, then the way to show undecidability is by comparing your problem to another problem that has already been proven undecidable. We do this by providing a map called a reduction that incorporates another problem into your problem. And since that problem that we map into it is undecidable and it's now included in your problem, the problem TSP must be undecidable as well. So the hard work in proving that a problem is undecidable is in finding the correct undecidable problem and then constructing this map into the problem that you're interested in. And the undecidable problem that we used is about matrix product operators, or MPO, which is a type of tensor network. And it doesn't matter exactly right now what tensor networks are, but the question is about a tensor, which is like a matrix, but in this case with 4 indices, so like a 4-dimensional box of numbers, shown here in blue. And we can build chains of these tensors by multiplying them together and ask, is the chain of length n, defined by that tensor, positive for all n? We call this problem MPO, for matrix product operator. And maybe you already hear a similarity to our problem TSP. There we also want something to be positive for all n. Now, this problem has been proven to be undecidable by my supervisor, Gemma de las Cuevas, and her collaborators in 2016. And this was done by proving a reduction from yet another undecidable problem, like we also want to do now. And the problem they used was 0 in the upper left corner, which is a problem about matrices, which in turn has a reduction from another problem, and so on, all the way back to the mother of all undecidable problems, the halting problem. And our goal is, of course, to add another step to this chain with a reduction to our problem TSP. So that's our goal, find a reduction from problem MPO to problem TSP. Our result is, what we managed to show is that we have a reduction to a restricted version of problem TSP. So restricted problem TSP is an undecidable problem. So what is this? What restriction did we need to put? So remember that problem TSP asks, given a map P, is it tensor stable positive? Now the restricted version asks, given a map P, is it tensor stable positive on a specific restricted input, namely on the matrix multiplication or MAMU tensor. And this is why we call this problem TSP MAMU. So normally, to check tensor stable positivity, we need to check that if we put in a PSD matrix, the output will still be PSD. And if we do this for the second tensor power, it should still be like this. So if you put in a big PSD matrix here, it needs to come out a big PSD matrix here, and so on for every n. Now, however, for problem TSP MAMU, we only ask this property for these MAMU matrices, standing for matrix multiplication matrices. So we require that these MAMU matrices are sent to PSD matrices, and also bigger MAMU matrices are sent to bigger PSD matrices, and so on, but we do not require it for all the other PSD matrices that are around. And with this restriction, we managed to provide the reduction. So our result is that problem TSP MAMU is an undecidable problem. For our big implication to hold, however, we need, of course, that problem TSP itself is undecidable. And therefore, we try to extend this reduction by finding a new reduction, a new step in the chain, from the restricted problem to problem TSP. And we have shown, however, that this is not easily possible. So the most obvious way is to find a reduction that maps a map here, map P to a map P, but this reduction can never work. And why is this the case? Well, for no answers, there is not a problem. If a map is already not sending the MAMU matrices to something PSD, it is definitely not a tensor stable positive map. So the answer here is also no. But if the answer is yes here, and the map sets all the MAMU matrices to PSD matrices, it can still act negatively on some other PSD matrices. And therefore, we did not manage to show undecidability of problem TSP. So to conclude, we intended to prove the undecidability of problem TSP because it would imply existence of the non-trivial tensor stable positive maps and therefore imply existence of the non-trivial, of the NPT bound entangled states that people have been trying to find for a long time. Instead, we have proven the undecidability of problem TSP MAMU. Well, for future work, we can still try if there's maybe another undecidable problem more suited to build a reduction from, and in this way try to prove undecidability of the problem TSP still, with all the consequences that would follow. So we are not done with this open problem though, and in our paper we also present an entirely different approach, where we consider the problem not on the complex number C, but on the hypercomplex numbers. And in this exotic field there exists halos of infinitesimally small numbers that make everything glow. And this can be used to prove existence of our non-trivial tensor stable positive maps on this different field. implying also existence of undestilable NPT states here. And shortly I will make another video dedicated to all of these results. But in the meantime, you can check out our papers for more details and proofs, and also to see already what this hyperreal story is about. And please get in contact if you have any questions or remarks. See you again soon. Bye.